Welcome to Intermolecular Forces. So, we've talked a little bit about gases, and we need to know why the gases don't always act ideally. And we also want to then look at liquids and solids. So, the physical properties of gases, liquids, and solids can be explained using kinetic molecular theory. So, gas molecules are farther apart and don't interact with one another at low pressure and at high temperature. Gases are compressible. Gases take the shape of the container. So we can explain this because the gas molecules are moving independently. They aren't attracted to one another significantly. They aren't repelled from one another significantly. So because they have plenty of kinetic energy, they're going to move around, and any individual gas molecule is going to move around the entire container, which means that overall, the gas is going to take on the shape of the container. It's going to take on the volume of the container. It'll just expand until those gas molecules hit the walls of the container, because there's nothing holding them together. Liquid molecules, on the other hand, the ones in the middle here, are held together more tightly, but the molecules can still slide past one another. So, the assumption in kinetic molecular theory of gases that says that the molecules don't have significant attractive or repulsive forces, that's no longer at all valid. Now they have significant attractive and repulsive forces. The molecules attract each other significantly, so that most of them are in the liquid phase. They're not in the vapor phase. Because those molecules are held closely together, the molecules can move past each other, but they're not so much breaking all of their intermolecular forces. They're breaking just one or two, maybe, to move from one place to another. But when they go to the next place, they're forming more intermolecular forces with other molecules around that are surrounding them in that new location. So they're able to slide past each other, but they're not able to move totally independently of one another. They're attracted to each other. But they're also being repelled from one another. They're not able to crush together and occupy a tiny space. They're repelling each other to some extent. And so this is why liquids are incompressible or just barely compressible. So if you take, say, a bucket of water, if you slap your hand down on the top of it, your hand hurts if you hit it hard enough, because that water is not compressing. Whereas if you do the same thing in air, your hand doesn't hurt because the air just moves out of the way or it compresses in front of your hand. Not proof for this well enough, but so solid molecules are also packed closely together and they can't move. But in this case, now the molecules can't move past each other. They're locked in place, which means that the solid is incompressible. The molecules aren't going to move at all, but the shape is also fixed. The molecules on the outsides, say, aren't going to move down or whatever and take on the shape of the container. So if we want to convert a gas into a liquid or solid, we have to take our gas molecules and get them closer together. We have to squeeze them together. And we can do this in two ways. We can either increase the pressure to force those molecules closer together, or we can decrease the temperature so that as the molecules pass each other, they start to interact with one another and they pull each other together then. And if we decrease the temperature low enough below the boiling point, then the gas molecules will pull the other molecules together and they'll coalesce into the liquid state. And then if we continue going, then it will eventually freeze into the solid state. So we can look at intermolecular forces. So intermolecular, meaning between, like international. Intermolecular means between two molecules. This is a force that's acting between two molecules. That they may or may not be of the same compound. They don't have to be of the same compound. Most of the time we talk about the intermolecular forces in chemistry, at least in a general chemistry class. Most of the time we're talking about forces from or between molecules of the same substance, but every once in a while we talk about between molecules of different substances. So we usually, by intermolecular force, we usually mean attractive forces, but there are some repulsive intermolecular forces. Essentially, once you get those molecules so close together that now they're trying to occupy the same space, then they'll begin to repel each other. But most of the time, when we say intermolecular force, we usually mean attractive force. So from here on, whenever I say there's an intermolecular force, I'm going to mean an attractive force, unless I specify that it's a repulsive force. So we have various types of intermolecular forces. We have van der Waals forces, which are dipole-dipole forces, London dispersion forces, or sometimes just dispersion forces, hydrogen bonding forces, and then we also have ion-dipole forces. So van der Waals forces are the intermolecular forces that exist between neutral molecules, in other words, not between ions. So these are the dipole-dipole forces, London dispersion forces, and hydrogen bonding forces. So dipole-dipole forces are the force between two neutral polar molecules. So the polar molecules each have a partially positive end and a partially negative end of the molecule. So if we have, say, two hydrogen chloride molecules, we've got a hydrogen chloride molecule here, the hydrogen is bonded to the chlorine. Note that this, the bond length is sort of artificially lengthened, it seems awfully long. So the hydrogen atom is significantly less electronegative than the chlorine atom is. So in this bond, we have a very polar bond. So if we draw this with our dipole in there, we have the positive end over here and the negative end on this side. So the chlorine becomes partially negatively charged, the hydrogen becomes partially positively charged, and we have the same thing occurring here. So we have our dipole pointing that way, pointing towards the chlorine, towards the partial negative end and away from the hydrogen. Well, what happens here is now we have a partial negative charge there and we have a partial positive charge here, and this negative charge and positive charge, the partial negative, partial positive charge, those will interact with one another, they'll attract each other. And so now we have sort of a link, we have an intermolecular force between these two molecules. Now, around them, there would be other molecules, and so this chlorine atom with this partially negative charge would be attracting other hydrogen atoms, and the same thing with this one. And there may be other partially positive ends, the hydrogen ends of other molecules also attracted to this chlorine. So it's not like this chlorine can only attract one hydrogen end of another hydrochloride molecule. So dipole-dipole forces are weaker than ion-dipole forces because an ion is stronger than a dipole is, because the dipoles are just partial positive and partial negative charges. So if you have an ion-dipole force, you have a total complete charge of +1 or -1 or +2, -2, and so on. Not just a partial with another partial. You've got a partial with a full complete. So the force is going to be stronger. And of course, our dipole-dipole forces are going to increase with increasing polarity, because then the dipoles get stronger. That partial charge becomes closer to an integer value. And so, of course, as the dipole gets stronger, our dipole-dipole interactions will increase. And for molecules of similar polarity, those with smaller volumes have larger dipole-dipole interactions. So basically, the closer you can get your dipoles together, the stronger they will interact with one another. Which seems to make sense if you have two magnets and you've alternated the ends, so the north pole of one is attracting the south pole of the other. As you get those closer together, then that attractive force will be higher. The same thing is true for our dipole-dipole forces. As we get our molecules smaller, then the dipoles can get closer together, and the dipole-dipole interactions will get stronger. So for something like water is a dipole-dipole interaction. Hydrogen chloride is another one. Hydrogen chloride will have dipole-dipole interactions with water as well. So that was dipole-dipole forces. So now let's look at the London dispersion forces, also sometimes just called dispersion forces. So with dispersion forces, this is the attraction between two neutral non-polar molecules. So you might be asking yourself, well, if they're non-polar and they're neutrally charged, why are they attracting each other? And that's a good question. Well, it turns out that these are the weakest of all the intermolecular forces. They're really quite weak. And this is because we have two neutral nonpolar molecules that we wouldn't normally think of as being able to attract one another, except that they can. Now this occurs because the nucleus of one atom attracts the electrons of the adjacent atom. And for an instant, the electron clouds become distorted. So we start out, and as we get our atoms closer together, the nucleus of one atom will interact with the nucleus of the other atom. And so let's move these molecules closer together. And now this nucleus begins to affect that molecule. And so just for that instant, as the electron cloud becomes distorted, as the electrons bounce around and sort of move around the atom, if we have a little bit more electron density around this atom than we do around this one, then we have sort of an instantaneous dipole that forms. It's only going to exist for a very short period of time, and then it will go away as the electron density rearranges itself again. But in that instant, now we have another molecule nearby. Well, now this molecule sees a dipole over there. And so this end of the molecule, the one that's closer to that partial positive charge, some of those electrons in the second molecule will move over towards the left side, towards the side that is closer to this positive charge. And so now this molecule gets a dipole in it as well, and that's called an induced dipole. It's being induced by the instantaneous dipole of the other molecule. So the instantaneous dipole induces this second dipole, an induced dipole in the other molecule. And because all molecules are composed of positively charged nuclei and negatively charged electrons that will move around randomly, that means that all molecules can do this. All molecules are able to have, for just fractions of a second, an instantaneous dipole. And that means that they can all induce a dipole in another nonpolar, uncharged, neutrally charged molecule. So that means that every molecule can have dispersion forces. They can all attract one another, even if they're not charged, because for just a split second, you create an instantaneous dipole, that then influences the dipole to form in the other molecule, and now those two dipoles will attract each other, just like dipole-dipole interactions will. Now, those dipoles are going to be very weak, because they're not going to last very long. But that attractive force will still be there. So, those two temporary induced dipoles will attract each other. Those two molecules will have an attractive force pulling them together. So London dispersion forces exist between all molecules, and this means that there are no ideal gases, because an ideal gas has no attractive forces. But there can't be any molecules that don't have dispersion forces. So there can't be any ideal gases. Every gas has to be an ideal gas. So what affects the strength of our dispersion forces? Well, the distance. The molecules have to be very, very close together. The farther they are apart, the weaker these intermolecular forces will be. And this is why at low pressures, the ideal gas law works just fine, because these dispersion forces are very, very weak to start off with, and the farther apart you get your molecules, because if you lower the pressure, the molecules will be on average farther apart. The farther apart you get your molecules, the weaker these attractive forces will be. So another thing that influences the strength is polarizability. Now this is the ease with which an electron cloud is deformed. The easier you can deform the electron cloud, either to create the instantaneous dipole in the first place or to create the induced dipole, the easier it is to polarize the molecule, the stronger these forces will be. So the larger the molecule is, the greater the number of electrons that the molecule has, the easier it's going to be to polarize the molecule, which means the stronger these intermolecular forces will be. So in general, the number of electrons increases as the molar mass increases, which means the polarizability of our molecule increases as the molar mass increases. And it also depends somewhat on the shape of the molecule, how the atoms are bonded together. So if you have, say, a greater surface area available for contact, so if you have something like this, where you have pentane, you have a long chain, and you have another long chain next to it. There's a lot of surface area there. There's a lot of availability for polarizing to occur, for the dispersion forces to occur. If you have a more spherically shaped molecule like this, so this is N-pentane and this one is neopentane. In this case, the polarizability is much less because now you have a spherical molecule. The contact area is going to be much less. And if you make the molecules even longer, you could imagine that this molecule gets sort of like spaghetti-like, and they'll intertwine with one another, and forces get even higher. All right, so that was dispersion forces. So now let's look at hydrogen bonding forces. So, with hydrogen bonding, this is a special case of dipole-dipole interaction. It's really just dipole-dipole interaction is just really, really strong. So, in this case, you have to have a hydrogen atom bonded to a small electronegative element, so fluorine, oxygen, or nitrogen. And you have to have an unshared pair of electrons on a nearby small electronegative element. So you have to have a fluorine, oxygen, or nitrogen bonded to a hydrogen, and you have to have a lone pair on that fluorine, oxygen, or nitrogen, or on a fluorine, nitrogen, or oxygen. It doesn't have to be that same one. So in the case of water, we have something like this. So we have a hydrogen bonded to an oxygen. The hydrogens become partially negatively charged. The oxygen becomes partially positively charged. The oxygen has a lone pair. So this oxygen has a lone pair that can attract this hydrogen and form a hydrogen bond. Now, hydrogen bonding is very strong compared to other intermolecular forces. And this is because electrons in the XH bond, so the oxygen, hydrogen, oxygen, nitrogen, fluorine bond, lie much closer to the X, to our very electronegative element, than they do to the hydrogen, which means that it's a very, very, very polar bond. It's basically almost an ionic bond. And this means that the hydrogen has a partial positive charge that's very close to 1, because it's almost ionic. And this means that our X atom, our electronegative atom, has a negative charge that's very close to -1. And so bond energies are between 4 and 25 kilojoules per mole. So this is weak compared to ordinary chemical bonds, where like that oxygen-hydrogen chemical bond, that covalent bond, is 463 kilojoules per mole. So this is maybe 1 to 5% of that. So it's a much longer bond, it's much weaker than this bond. The hydrogen bond is much weaker than the oxygen-hydrogen covalent bond is, but it's still fairly strong compared to most other ionic bonds. All right, so now let's look at the ion-dipole forces. Now we talked about these a little bit with the dipole-dipole forces, and we said that the dipole-dipole forces are much weaker than the ion-dipole. So, ion-dipole forces, this is the attractive force between an ion and a polar molecule, or a dipole. So if we have something like water, and if we put sodium chloride into water, right, we've got a sodium ion here and a chlorine ion there. The chloride ion has a negative charge to it, while the partial positive charge of the dipole that's around the water molecule. The water molecule has a partial positive side. The partial positive side, so the hydrogen ends are going to point towards the chloride molecule, towards the negative chloride atom, chloride ion. And over here, we're going to have the positively charged sodium ion having the negative ends of the water molecules pointing towards it. So here we have the oxygen side pointing towards the sodium, and there we have the hydrogen side pointing towards the chloride. So, let's look at the strengths of our intermolecular forces. We have dispersion forces. Those are very, very weak, but every molecule can do them. Then we have the dipole-dipole forces. They're stronger than the dispersion forces, but only polar molecules can do this. Then we have hydrogen bonding. That's basically really strong dipole-dipole bonding, where you have to have a hydrogen bonded to a nitrogen, oxygen, or fluorine, and you have to have a nitrogen, oxygen, or fluorine with a lone pair of electrons that may or may not be the same atom as the one that's bonded to the hydrogen. It's basically really, really strong dipole-dipole bonding because it's almost an ion. And then you have the ion-dipole bonding, and of course that's going to be stronger than the hydrogen bonding because you have an actual ion. You have a full and complete ionic charge there that's bonded to the dipole. Now, these are all of these intermolecular forces are very weak compared to the covalent bonds within molecules and the ionic bonds between the ions. Those are much, much stronger, but the strength increases as you move down on this slide. So that was intermolecular forces.